Okay. Just hold on a second. Okay, so let us start. So last time we had started discussing vectors and tensors, and so what we said was that in the 4D Minkowski space, a vector has four components, and we often refer to it as four vector. Vectors form a linear algebra and constitute a vector space. So if V is a vector and A is a real number, then A times V is also a vector, and it's in the same direction for A greater than 0, but its magnitude is multiplied by A. That is how the usual vectors were also defined. Only difference now is that we haven't defined any coordinates with respect to which we are defining vectors, and we have not defined any transformations as to if you do change of coordinates, how you would transform. Nothing is defined right now. Just use notion of vectors to define a vector space. And the reason we can do this is because we define quantities like vectors, scalars, and as we will define later, tensors to be quantities which are independent of choice of coordinate system. And that is the reason why they are useful. Of course, there are quantities which do depend on choice of coordinate system, and they are also useful, but in a different sense. So typically in physics, we exploit both these properties. If you want to write down some laws of physics or some quantities which are independent of choice of coordinate systems, you would want to write them in terms of quantities like scalars, vectors, and tensors. And therefore, it doesn't matter if you understand them in one coordinate system, their behavior would be same in any other coordinate system. On the other hand, there are quantities which do depend on coordinate systems, and we exploit those also by saying that, like, I choose an appropriate coordinate system in which that object becomes simple, so that we can do a calculation by setting that object to a simple expression, or sometimes even to 0. And then once you compute that result, then you could kind of generalize it to any other coordinate system by just doing coordinate transformation. Okay. So that is the kind of advantage of having quantities which can be defined independent of choice of coordinate systems, wherever laws of physics you want to kind of state that these kind of quantities would be useful. Okay, so it is one thing to say that the vectors are invariant under coordinate transformation, but that does not mean that the components of vectors are invariant. So what happens is that although the vector is invariant, components do transform. So if you do coordinate transformations, then the components do transform, and we will see exactly how they will transform. Okay. Another thing is that, like, we in Cartesian coordinate systems, we are used to defining vectors as some kind of an arrow going from one point in space to another point in space. And that is kind of a bit of a misleading notion, because there is no such invariant meaning to an object defined from one point in space to another point in space, except, of course, in the flat space. Where you can define a metric which is really independent of space-time. Okay, so the kind of spaces that we would be interested in, it is better to define a vector at a given point in space and time. Okay, and therefore, every time we will be talking about vectors, we will be talking about vectors with respect to a particular point. Okay, so that point is typically called the base point, and what we will do is to look at the space of vectors, which is typically called the tangent space at a point, and we say that all vectors are defined as vectors in the tangent space at a given point. So if we have a point P, then we define a tangent space TP, and all the vectors defined at base point P are vectors which are written in terms of vectors in the tangent space. Okay. So one way of kind of asking what are the vectors that are there in the tangent space would be to say that all kinds of 4 vectors that you could define at a point P would define a tangent space. Okay. Now, of course, the number of vectors that you would define at a given point P in any dimensions is typically infinite. Okay, unless you are in, say, 1 dimension, or even in that case, you have magnitudes possible, but you don't really need to define that many vectors. Any arbitrary vector should be definable in terms of finite set, which we'll come to in a moment. Okay. So what we are going to do is to use this notion of vector space defined at a particular space-time point. Okay, but that notion is very restricted, because every time you want to talk about something, you have to go to a particular point and compute. Okay, what we want to really do is to define what a quantity called a vector field, and a vector field is an object where you assign a vector at every space-time point. Okay, so at every space-time point, you have a tangent space. You pick one vector from every space-time point. Okay, so that is the notion that one is going to use. Okay, fine. So given the fact that tangent spaces defined at different points are different vector spaces, there is no simple notion of comparing these vectors with each other. Okay, so as a result, we will have to kind of wait for defining some notion which will allow you to compare a vector defined at one location to another location. Okay, so until we do that, we would basically be talking about vectors defined at a particular point. Okay, now tangent space TP at a point P is a vector space, and that's kind of trivial thing to see, in the sense that, like, if V and W belong to the tangent space and A and B are numbers, real numbers, say, then A plus B times V plus W has a distributive property, and it would be A times V plus B times V plus A times W plus B times W. And that would be another vector in the tangent space, simply because, as I said, that all possible 4 vectors at a particular point constitute a tangent space. So if V and W were some 4 vectors, then this linear combination is another 4 vector, and therefore it should be part of TP. Okay, so in that sense, it forms a vector space. Now this vector space, we'll have to kind of give a notion of inner product in this vector space, and so we can do that. But before we do that, let's first define basis vectors. Okay, and this is something which I was saying some time ago, that even if you have infinite number of vectors defined at a particular point, they can be described in in terms of finite number of basis vectors. Okay, so basis vector is any set of vectors which span the vector space. That means any vector in a vector space can be written as linear combinations of these basis vectors, and these basis vectors themselves are, of course, linearly independent. Okay, so you don't do overcounting out there. Okay, so yeah, so once we have a basis, then, as I said, any vector could be described in terms of that. Okay, now how many bases that we can define for a vector space? Well, you can make any choice, so there are like infinite possible bases. It may not be possible to have all of them very convenient to use, but depending upon the problem that one is looking at, a particular basis could be convenient. It's exactly the same as what we do in, say, quantum mechanics. For example, if you want to solve say, a hydrogen atom problem in quantum mechanics, you realize that it has spherical symmetry, and therefore in three-dimensional space you would choose a spherical coordinate system, and that is a convenient basis compared to, say, Cartesian coordinate system. And then you suddenly realize that, like, well, spherical coordinate system is good, but parabolic cylinder coordinate system is even simpler. Okay, so you could do that. Okay, so, but which coordinate system would be best suited is a priori hard to guess. Okay, spherical symmetry of the problem did tell you that the spherical coordinate system would be useful, but that there could be something even simpler than that is not something which is immediately obvious. Okay. Fine. So let us define basis vectors for the tangent space. So let E hat alpha be a set of basis vectors of the tangent space at point P. Then any vector A which belongs to TP can be written as A alpha E hat alpha. Okay, so this is how you would decompose a vector in terms of basis elements and the components of the vector. So we would call A alpha as components of the vector A. A typical example of a vector is a tangent vector to a curve. So suppose we have a x alpha lambda which parameterizes a curve in space-time. So lambda is a parameter which can vary from, say, 0 to 1 or 0 to any value, say. Okay, and as you change lambda, for different values of lambda, you are assigning different space-time points. Okay, so if this parameterization is continuous, you would say that you have assigned a curve called x alpha lambda, which is a kind of a smooth function of lambda. For this curve, you can define a tangent vector by just saying that as you change lambda infinitesimally, how does x alpha change? Okay, and that is by v alpha, which is a tangent vector, which is defined as dx alpha by d lambda, and which is v alpha is a component of tangent vector, and v lambda is the tangent vector, which is written as v alpha lambda times e hat alpha, where e hat alpha is just a basis. So therefore, all these components are kind of collected together, written in terms of basis to write down the vector. Okay, so suppose we do a Lorenz transformation. Okay, then under the Lorenz transformation, we have x alpha going to x prime alpha prime. Okay, which is a Lorenz transformation matrix lambda times x. Okay, it's a linear transformation, and under that transformation, v lambda is invariant. Okay, as I said, that the vectors are invariant, and therefore v lambda would be invariant, but the components would transform. Okay, and that is kind of easy to see. You look at this definition, and you can easily check that under this coordinate transformation, this definition would transform as v alpha going to v prime alpha prime, which is lambda alpha prime beta times v beta. Okay, but as I said, that v lambda is invariant. Okay, but the components transform. So only way you can arrive at invariant definition is to say that E hat alpha transforms in the opposite fashion. Okay, so the transformation of E hat prime involves lambda inverse, such that the expression defined here, V alpha E hat alpha is invariant. Okay, with V alpha transforming by lambda and E hat transforming by lambda inverse. Okay, so this also defines the way the basis vectors of the tangent space would transform. Okay, now of course this is for Lorenz transformation, but there is nothing special, particularly when you are looking at vector spaces. There is nothing very special about Lorenz transformation. So we can in principle consider arbitrary transformation x alpha to x prime alpha prime, which could be a very complicated function of x alpha. Okay, which we would call general coordinate transformation. And if you do a general coordinate transformation, x alpha goes to x prime alpha prime, which could be a complicated function of the original coordinates. Then under that coordinate transformation, v alpha would go to v prime alpha prime times del x prime alpha prime by del x beta times v beta. Okay, it's kind of trivial to check that if del x prime alpha prime is a linear transformation like this, then if you take this partial derivative, you actually get this Lorenz transformation parameter lambda. Okay, And this inverse transformation of the basis vectors shows up as the inverse element dx beta by dx prime alpha prime multiplying e hat beta. Okay. So any questions about this? Okay. So maybe I proceed ahead. So let us so as I said, like this transformation for linear transformation would give you a Lorenz transformation matrix. So let's now do one more thing. Let us define an associated vector space called the dual vector space. Okay. So the dual vector space to a tangent space TP at point P is called the cotangent space. Okay. And it is generically denoted as T star P. Okay. Fine. Now the dual vector space is a vector space of all maps. And these maps do the following thing. They pick up a vector from the tangent space and give you a number. Okay. So all these maps which define the dual vector space they also have another name. They're called one forms. Okay. So so the basis vectors, the vectors of the dual vector space are also called one forms. Okay. And they are generically denoted in the following way. They are called, if say omega belongs to T star P and V and W belong to the tangent space TP, then for any AB real, omega A times V plus B times W, this is the action of omega on the tangent space vectors, is A times omega acting on V plus B times omega acting on W. Okay, so in some sense, omega has a linear action on the vector space and it acts only on the vector space elements and not on the scalars. Okay, but as I said, that the property of the dual vectors is that they map original vectors to real numbers. Okay, so therefore omega v as well as omega w are just real numbers, and therefore A times omega v plus B times omega w just belongs to a real number. Okay. So therefore, we can use this notion to define some kind of a inner product between a vector space and the dual vector space. Okay. Now, the dual vector space T star P is also the dual space T star P also is a vector space, and that also you can kind of check by doing this thing, that you take a linear combination of two one forms or two dual vectors, okay, and see their action on a particular vector in TP, and that property has a distributive property, and this vector, dual vector rather, can be written as A times dual vector acting on V plus B times dual vector eta acting on V, and omega V and eta V both are numbers, and therefore this right hand side is just a number. Okay, fine. So the way we define E hat for TP, we need to define similarly dual basis for T star P, and we will call that theta hat. And notice that unlike E hat, which has subscript indices, theta hat has superscript indices. And that is simply because the components of the vectors belonging to T star P have indices downstairs, okay? Subscript instead of superscripts. Okay, so what we have is a new basis defined for the T star P, which is theta hat, which has a property that theta hat on acting on E gives you a number. Okay, if you choose a correct basis, then you can just diagonalize this and you can say theta hat alpha acting on E hat beta is just delta alpha beta. Okay, and then a generic one form or generic dual vector can be written as omega alpha theta at alpha. Okay, exactly the way the vector V was written as V alpha E hat alpha. Similarly, the dual vector is written as omega alpha theta hat alpha. Okay, is this okay? Any questions? Okay. So let's go ahead. Um, Notice that the components of vectors belonging to the tangent space TP have indices sitting upstairs, and therefore we would say that those components transform contravariantly. And because the components transform contravariantly, the vectors themselves are called contravariant vectors. Okay, so as I said, vectors itself does not transform, but its components transform contravariantly, and therefore that vector would be referred to as a contravariant vector. On the other hand, the vectors belonging to the dual space, which is the cotangent space, they have transformation in such a way that the components transform covariantly, and therefore we call them covariant vectors. Fine. Now let us try to understand this inner product that we have written down, omega acting on V, and that could just be written as omega alpha theta hat alpha times V beta E hat beta. Fine. But this action is completely determined by how theta acts on E. Since theta hat alpha on E hat beta gives you delta alpha beta, we can use that relation to write down the action of the basis vectors on each other to be equal to delta alpha beta. And then we can use that to write down omega acting on V as omega alpha V alpha. Okay? And this, of course, is a number. Okay, so that is how you define the inner product between the dual vector space, which is called a cotangent space, and the tangent space. Okay, now one could, of course, have an opposite point of view on this one, and we can think of the original vector space. There's a typo here, I'll correct that. The original vector space as a space of maps on the dual vector space. So instead of writing omega of V, we can write that as V of acting on omega. And this quantity should also give you the same answer. Okay, so there is a dual relationship between the tangent space and the cotangent space. And the property of these two vector spaces are such that if you dualize the vector space twice, so you dualize once, you go from tangent space to cotangent space. But if you dualize it once again, you're back to the tangent space. Okay? Fine. Okay. So although we have been studying vector spaces defined at a single point, we would be interested in vector fields and dual vector fields which are defined on the entire space-time. Okay, and in this case, the action of dual vector field on the vector field, unlike the way we had defined for dual vectors and vectors, which are defined at a particular point. Okay, so this action gives you a number. Okay, but this is a number associated with a point P. Okay, now you define similar tangent space at some other point, say P prime. Okay, where you have another vector V prime and a dual vector, say omega prime. Then omega prime acting on V prime would give you omega prime alpha V prime alpha. That is again a number, but it could be a different number. Okay, and therefore at different space-time points, this inner product belonging to the corresponding tangent and cotangent space would give you different numbers. As a result, the dual vector field acting on a vector field will not give you a number, because that would mean that all such inner products will give you the same number, but instead it would give you a function, or it would give you what is called a scalar field. Exactly the way vector field is defined as an object which is which is an assignment of a vector at each space-time point. Like that, scalar field is an object where there is an assignment of a number at each space-time point. That number doesn't have to be same everywhere. If it was same, then of course it would give you the answer that your scalar field is constant. Okay, but that is not necessary. Okay, fine. So of course, scalar is a quantity which has no space-time index. So therefore, that is kind of consistent with this inner product that we are defined. Okay, which of course does not have any space-time index because the index alpha is actually contracted. Okay, so there's a small exercise that you could do at this point, and that is find the transformation properties of omega alpha and theta alpha under arbitrary transformation, which is what we call general coordinate transformation, x alpha to x prime alpha prime, which is an arbitrary function of x alpha. Okay, so of course by arbitrary we mean the function which is kind of invertible, so that you can kind of under the transformation you should be able to kind of go back to the original coordinate system. Okay, fine. So a typical example of a dual vector field is the gradient of a scalar field. Okay, so consider phi to be a scalar field. That means phi is an assignment of a number at every space-time point. Okay, and you look at that kind of object where a number is assigned at every space-time point, and you ask, what if I study the gradient of this object? Okay, then that gradient is defined as del phi by del x alpha times the dual vector basis of the dual vector space, okay, which is theta alpha. Now, if you do a coordinate transformation, then you can check that by chain rule, d phi by dx prime would be, sorry, del phi by del x prime would be del phi by del x times del x by del x prime. Okay. Now notice that this del x by del x prime is precisely the kind of transformation that we had seen for omega. Okay. That is how it would have transformed. Well, I think I did not define it. Yeah. Yeah, I'm sorry, I did not define for omega, but it is defined for theta. The theta would transform in such a way that this transformation is invariant, okay? And as a result, omega would transform in the opposite fashion, okay? So maybe I will write down those transformations explicitly, okay? Fine. So any questions at this point? Okay, so maybe I'll continue and let us talk.
So,
Yes.
Initially, the vectors that you were describing, you were calling them some v of lambda, where the components are v mu.
Yes.
And but in I mean, it's fine as a definition, as an abstract definition, but in actuality what we are associating our physical space space time is with those components only, right? The v of lambda does not have any significance physically speaking.
Well, that is not true in the sense that, like, even in Cartesian coordinate system, whenever you wrote down vectors, you said that x I hat plus y j hat plus z k hat, right? That is how the vector was defined. And the way x y z transformed under coordinate transformation, okay, I hat j hat k hat transformed in the opposite fashion, right?
Yeah.
So we are doing the same stuff now. Okay, it is just that, like, we are giving a generic definition instead of I hat, j hat, k hat. We just say e hat alpha. If you take Cartesian, then they are I j k. If you take spherical polar coordinate system, then they are theta phi and so on. Okay, so this is a generic definition. But yes, every time you look at the transformation property, you always look at the components of the vector. Okay, and you don't worry about what happens to the basis vectors. Okay.
Yeah. Okay.
Any other question?
Sir, when we say that the vector transforms in a particular way, do we have a specific basis in our mind?
No,
Uh,
in fact, that is the point. That is how I started my definition of vectors. That vectors are are objects which do not transform under coordinate transformation. Okay, and that is the reason uh, why I write down V lambda as an object which does not transform, but V alpha lambda, which is a component of the vector, does transform. Okay, and its transformation property is independent of choice of basis vectors. Okay, only thing that is important here is that the basis vectors transform in the opposite way. That is all that is important here. Okay, so the transformation property of vectors or scalars or tensors is defined once and for all. Namely, under coordinate transformation, they don't transform. Okay, but then the basis vectors that we use for defining the components of these objects, those basis vectors transform, and therefore the components also transform. Okay.
So under a coordinate transformation, when we say that phi mu goes to phi prime mu, which is say x mu prime by x nu bhim nu,
This one, yeah.
then yeah, that is for a coordinate basis, right? Will it hold for other type of transformations or other type of bases?
This is true for any basis. It doesn't matter what.
This is true for any basis.
This is true for any basis, yeah. It doesn't matter what choice of basis you have, as long as that basis defines a space, and that basis is linearly independent and spans the vector space, it is fine. There is no question about that. So only two things that are important, and that is that the basis that you choose is linearly independent and spans the vector space. Okay, so that you don't have redundant vectors. Like you are working in 4 dimensions, you don't write down 5 vectors. Okay. So that is the linear independence condition. And if there are 4 of them, they should, and linearly independent, they span the space. And the second statement, just to be on safer side, is to say that the general coordinate transformation that you are considering is invertible. Okay. By invertible, I mean that if you do a coordinate transformation, it can take V beta to V prime alpha prime. But it should be possible for you to get back from V prime alpha prime to V beta. Okay. So barring that, there is no condition on what basis you choose and what coordinate transformation you choose.
So any abstract vector, I can write it as v mu times or some e hat mu,
Yeah,
right?
absolutely, yeah.
So when we are doing a coordinate transformation,
Yeah.
I mean the vector has to know, right? We're doing a coordinate transformation. So how does it? I mean, how does it know that we are doing a coordinate transformation? So doesn't that information we have to put somewhere in the basis or some?
Yeah, so the information is there in the basis vectors, right? So for example, you would have done this in when you studied, say, curvilinear coordinate systems, that if you work in I hat, j hat, k hat basis, which is Cartesian basis, to r hat, theta hat, phi hat basis, then you need to define what are called direction cosines. Okay.
Right.
And the direction cosines are the ones which tell you how one basis is related to another basis. Okay.
Right.
These direction cosines are basically these del x prime alpha prime by del x beta in some sense. Okay. And you can use those direction cosines to write down, say, a Laplacian operator or a gradient operator and so on. Okay. What we are doing is that, like, we are not working in curvilinear coordinate system, but we are working with arbitrary coordinate system which could be curved also. Okay, curvilinear coordinate systems are the coordinate systems where the variables chosen in such a way that the coordinate seems to be curved. Okay, but actual space is still flat. Okay, as against the kind of coordinate that we would be considering is the coordinate system or the space itself would be curved. Okay. So therefore, we, instead of working with direction cosines, we work with the way the components of a tensor would transform directly. Is that okay?
Okay. Okay.
Any other question? Okay, so maybe let's get back to what we're talking about. And that is, we generalize this notion from vectors and dual vectors to tensors. Okay, so tensors is nothing very kind of dramatic from whatever we have just studied. Only difference is that vectors carry, or other components of vectors carry single index. Okay, scalars do not carry any index. Tensors carry indices which are more than one. Okay, so nothing very special really. One could have even called vectors. Vectors also could have been called tensors, and we will see in a moment by when we define tensors how we could kind of name vectors also as tensors. Okay, fine. So tensor is in some sense a generalized notion, and it's an object which carries multiple space-time indices. Okay, and in addition, it transforms homogeneously under coordinate transformation. Okay, now this is a very important point, because without this statement, the object that would carry multiple space-time indices does not define a tensor. As we'll kind of, as the course progresses, you will see that there are objects that we will define on space-time which carries multiple space-time indices, but they are not tensors. Okay, so simply because some object has multiple indices does not necessarily mean that it is a tensor. Okay, now remember that when we are looking at vectors, we had two types of objects, vectors and dual vectors. Okay, and they had the property that their components would either have contravariant index or could have covariant index. Okay, but if you have multiple indices, imagine you have some object which is not a single index object but two index object. For example, suppose you have some V alpha beta, then you have multiple possibilities, because you could have a V alpha beta both alpha and beta contravariant, or you could have V alpha beta with both alpha and beta covariant, or you could have alpha contravariant and beta covariant. Okay, now that kind of possibility which exists for generic tensor, okay, does not exist for vectors. Okay, so we define tensors into, categorize them into three types. What we call covariant tensors. Covariant tensors are the tensors whose components have subscript indices, okay, which are typically called covariant indices. And these are the objects defined in the cotangent space, okay, because the basis vectors are theta hat. Fine. Now you can clearly see that given the covariant tensor defined this way, and it has kind of subscript indices alpha 1, alpha 2, dot, 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 it could of course have only one subscript index, namely alpha 1. Okay, and then there is of course it is multiplied by theta hat alpha 1, and there is no theta hat alpha 2 onwards. All ellipses are also missing. That is an object which is a well-defined tensor, but it carries only a single index, and that is something we would call a covariant vector. Okay, a vector which belongs to the cotangent space. So tensors is a more generalized notion, which of course incorporates vectors inside it. In fact, you may have a tensor which carries no index on it, and therefore there is no theta or e multiplying that. And that is also a tensor carrying no index, and which is what we would call a scalar. Okay, is that fine? Okay, I just need a small response. The power has failed here. I just want to be sure that we are connected.
Yes,
Okay, great, thanks. Okay, so the way we define covariant tensors, we could have also defined contravariant tensor, exactly the way I said, that you could have all the indices sitting upstairs and they are part of, oh boy, there's a typo, it should be E hat here. Okay, so yeah, fine. So so you could have a T alpha 1, alpha 2, dot, 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 E hat alpha 1, E hat alpha 2, dot, 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 kind of thing, which is a member which would belong to the tangent space. Now notice one thing, that when I say they belong to tangent space, these objects actually do not belong to the tangent space per se. In the sense that like anything which would belong to tangent space would be a tangent vector, or anything which belongs to cotangent space would be a cotangent vector. Okay, these objects are objects written in, which are linear objects with respect to say e hat or theta hat. Okay, whereas tensors are not linear objects. They are like tensors carrying more than one indices are quadratic or cubic in theta hats or e hats. Okay, and as a result, they are not really, do not really belong to tangent space or cotangent space, but they belong to products of tangent spaces and cotangent spaces. Okay, we'll come to that in a moment. Okay, so besides defining purely covariant tensors, which are kind of relatives of dual vectors, and purely contravariant tensors, which are relatives of tangent space vectors, you could also have mixed tensors, which have few covariant indices and few contravariant indices. And they are, of course, appropriately contracted with alpha 1, alpha 2 dot contracted with thetas, and beta 1, beta 2 dot contracted with e hats. Okay. So with these kind of definitions, you can see that like whether it is a covariant, contravariant, or mixed tensor, none of them transform into coordinate transformations. Okay. Their components do, however. Okay. So once you define it in this way, it is better to kind of classify tensors by defining a notion called a rank of a tensor. So a rank of a tensor is equal to the number of irreducible indices on the components of the tensor. Okay. So I'll come to that in a moment. But suppose you have a tensor, say, which is covariant tensor, and it has alpha 1, alpha 2 dot alpha n. Okay. Then you would call that tensor rank n covariant tensor. Okay. Similarly, if you have a T alpha 1, alpha 2 all up to alpha say k contravariant indices, then you will call it a rank k contravariant tensor. Okay. When you define mixed tensor, then things can get a bit tricky in the following way: that if alpha 1, alpha 2 goes up to alpha n, and beta 1, beta 2 goes up to beta say k, then this would be a tensor of rank n plus k in some sense. Okay, provided the indices which belong to the which are covariant indices and the indices which are contravariant do not get summed. Okay, so that is the notion of what we call the number of irreducible indices. Okay, so we'll come to that in a moment. Okay, but is this definition clear? Covariant, contravariant, and mixed tensors. You can see one thing here, that the notion of mixed tensor is something which we had not encountered so far. Because if you have a single index, it can be either upstairs or downstairs. And if you have no index, there is no question of it being anywhere. Okay, so therefore, our understanding of scalars and vectors would not have told us as to how you define mixed tensor. Okay, but it would have easily told us as to how you would define covariant tensors or contravariant tensors by just saying that you just allow more and more indices. Okay, so in that sense, there is one extra object that one needs to look at, namely the mixed tensors. Okay, fine. So let's go down and look at some examples. So T alpha beta with alpha beta indices downstairs are components of covariant second rank tensor if the following thing is true, that if T alpha prime beta prime as a function of x prime is related to T gamma delta as a function of x in this particular fashion, which is del x gamma by del x prime alpha prime times del x delta by del x prime beta prime. Okay. If you restrict these transformations to Lorenz transformations, then of course these quantities would be written in terms of lambdas, and that is the last piece. Okay. Of course, the middle piece, which is written out here, del x gamma by del x prime alpha prime type of stuff, allows you to do any arbitrary general coordinate transformation. Okay. The last piece is, of course, a restriction to Lorenz transformations. Okay, so this is how the tensor would, a covariant tensor would transform. In this particular case, we have taken a second rank tensor. Now notice one important thing here, which we'll kind of talk about later also, and in fact we will use this fact several times when throughout the course, and that is the following, that this transformation property guarantees one thing, and that is that if t gamma delta is equal to 0, say in some coordinate system, then that object is 0 in every other coordinate system. Okay, so therefore tensor has a property that if it is non-zero in some coordinate system, then it is non-zero in all other coordinate systems. Okay, and if it is 0 in one coordinate system, it is 0 in all. Okay, now a non-tensor of course is an object which wouldn't transform this way. Okay, and it may have a little different behavior. Okay, we will talk about it when we define what is called a non-tensor. Okay, so let us first get the concept of tensor clear. Okay, now instead of looking at the second rank covariant tensor, we could look at second rank contravariant tensor. And if you do that, then you can see that the contravariant tensor has the opposite transformation. Instead of dx gamma by dx prime alpha, you have dx prime alpha prime upon by del x gamma. Okay, and similarly beta prime and delta. Okay, but the property that I just mentioned about the tensor continues to hold, whether it was a covariant tensor or a contravariant tensor or a mixed tensor. Okay, that if it was 0 in some coordinate system, it would be 0 in all. Okay, the last piece again is the Lorenz transformation case. If you consider a mixed tensor, that means one index is upstairs and one index is downstairs, then its transformation property has one transformation which is del x prime by del x, and the other transformation is del x by del x prime with appropriate indices. Okay, and it gives you t gamma delta. Okay, fine. So now let us kind of, after having understood how the mixed tensor would transform, let us consider an object which is t alpha alpha. Okay, now remember when we looked at the inner product of a dual vector with the original vector, we said that omega acting on B gave us a number, and that number was defined as omega downstairs alpha with B upstairs alpha. Okay, if you want, I can just go back a little and show you that expression. It is this. This object, when you have indices repeated, okay, then the notation that we have been using, that the repeated indices are summed. Okay, so when we say, oh, wait a minute, this should have been omega actually. Omega alpha V alpha would mean alpha takes all possible values 0, 1, 2, and 3 if you are using Cartesian coordinate system, but any 4 variables that we have. Okay, so therefore all these indices are summed, and therefore there is no free index sitting around on this quantity, and therefore that is just a number at a particular space-time point. Okay, so similarly, if you are looking at T alpha alpha, this quantity is defined with alpha summed over. So this object actually does not carry any free index. Okay, and therefore, in spite of having 2 indices sitting around here, it is not a second rank tensor. And that you can see by just looking at how the second rank mixed tensor transformed and setting the indices appropriately. Okay, so suppose you look at T alpha prime, then its transformation is given by dx prime alpha prime by dx del x prime alpha prime by del x gamma, and del x delta by del x prime alpha prime. And you can clearly use a chain rule here to get rid of del x prime alpha prime piece, and once you remove that piece, you get del x delta by del x gamma. But within that coordinate system, that answer better be delta. G, I have it opposite. Okay. The answer should be delta upstairs and gamma downstairs. Sorry for several typos. This thing. And if that is the case, then this would give you t gamma gamma back. Okay, without any transformation function sitting around. An object which does not transform under coordinate transformation, okay, and of this type, okay, would be called a scalar. Okay, so therefore T alpha alpha is actually a scalar quantity. okay, in spite of it having some indices sitting around on it. Okay, so when we said that a rank is defined by the number of irreducible indices on the component of the tensor, we meant that a tensor carries all kinds of indices on it, but there are no covariant index is contracted with the contravariant index. If it is, then those indices should not be counted. Okay, so rank of a tensor depends on only irreducible set of covariant and contravariant indices. Okay, so what we will do is that we will denote these tensors by using a notation, say KL, okay, which represents K contravariant indices and L covariant indices. For example, T alpha beta would be called a 0,2 tensor because it is a covariant tensor. Okay, now it's a kind of bad notation nomenclature because tensor actually does not carry any index because these are the components of the tensor. But one uses a bit of a, it's a bit of a misuse of terminology, but one tends to call T alpha beta itself as a covariant tensor, covariant second rank tensor. Strictly speaking, we should be really calling it components of second rank covariant tensor. But okay, so T alpha beta therefore transforms as a 0,2 tensor because it has two covariant indices. And as I said, we would use KL as a notation to denote a tensor of rank contravariant rank K and covariant rank L. Since it has no contravariant index and two covariant indices, it's a 0,2 tensor. Similarly, T alpha beta with upstairs would be called 2,0 tensor, and damn, I'm sorry, just too many others. T alpha upstairs and beta downstairs is called a 1,1 tensor. Okay. As I said, I'll put up these notes in the Dropbox with all these typos corrected. I'm sorry for having multiple typos. I've been furiously typing them and haven't been getting enough time to do the proofreading of it. But the ones which I'll put up in the Dropbox would definitely have the corrected equations. And if there are any typos left over after that, please let me know. Okay. So fine. So any questions about this? Okay. Fine. So let's kind of generalize the concept that we had used last time, namely that the dual vectors were linear maps from the vector space, or from the say tangent vector space to real numbers. Okay, we will use the same kind of notion, but generalize it to tensors because tensors are objects which carry multiple indices, and therefore tensors are multilinear maps from a collection of vectors and dual vectors to real numbers. Okay. Now remember, we can have tensors of multiple types, right? We just saw terrible this thing, but I think I have this one which is without errors. Okay, so we just saw that we can have covariant tensors. Okay, and these covariant tensors can carry any number of indices on them. Then suppose they carry say n indices, then you need to take a collection of n vectors. Okay, then the covariant tensor acting on n vectors would give you a number. Okay. Similarly, a contravariant tensor with say k contravariant indices would act on k dual vectors and give you a number. On the other hand, if you have a mixed tensor, then of course you will need appropriate number of vectors as well as appropriate number of dual vectors, so that the action of the mixed tensor on them gives you a number. Okay. So the computation is to be done in such a way that there is no free index left over because when it gives you a map to a number, it carries no index on it. Okay. So what we are going to do is to think of tensors as multilinear maps from collection of vectors and dual vectors to a number. Okay. So if you have a KL tensor, then a KL tensor maps a collection of L vectors and K dual vectors to a real number. Okay. Fine. So this relation always goes opposite because the KL quantity, I think I'll try to put it in the bracket so that it will be consistent with this thing of writing 0, 2 with a bracket. So I'll put parenthesis to KL, this thing. But remember that K is the number of contravariant indices on the tensor. Okay, so therefore that is the number of covariant vectors you would need. But the covariant vectors are dual vectors. So therefore, if you have a KL tensor, then you need K dual vectors and L vectors. Okay, so therefore, the TKL, that means a tensor with K contravariant and L covariant indices, would take K copies of T star P times L copies of TP to a real number. Okay, so TP, as I said, TP occurs L times and T star P occurs K times. Okay. So I need to define what is the meaning of this product. So this product is defined in the following way, that if I say TP star TP cross TP, then I mean that this is a space of ordered pairs of vectors. So you take, of course, TP is the same vector space, but TP times TP is a space in which you write down two vectors, and it's an ordered pair. First vector belongs to first TP, second vector belongs to second TP. Okay, and this choice is important because the action of the tensor is defined in an appropriate fashion. Okay, we will do it in a moment. Okay, fine. Now we said that the tensors are multilinear maps. So I should define what multilinear means. So by multilinear, I mean that tensor acts linearly on each of its arguments. Okay, fine. So here is the object on which tensor is going to act. Okay, so this tensor would carry K contravariant indices. So say you look at the second contravariant index on that, then it will act on the second T star P occurring in this product. Okay, it wouldn't act on anybody else. Okay, and that action is linear action. That means the index, second contravariant index of T will act on second covariant index in the series of T star P. Okay, it is this notion which defines the multilinear action. Okay, any questions about this? And because of this way the multilinearity is defined, the way the tensor is written, the way the indices are written is important. You cannot shuffle the indices around unless there is a specific symmetry that the tensor would have. Okay, so we will talk about that in a moment. Okay, fine. So consider a 1,1 tensor. Then a 1,1 tensor, as you know, has one contravariant index and one covariant index. Okay, so therefore it would require one dual vector and one usual vector belonging to tangent space to give you a number. Okay, so the T, which is a 1,1 tensor, would have action on A omega plus B eta, which is some linear combination of cotangent vectors or dual vectors, and would have action on CV plus DW, where V and W are tangent space vector, and the action is linear on each one of them. So therefore, T would pull A and C out, okay, times T omega V plus A times D which will give you omega W, and B times C, which will give you eta V, okay, and B times D, which will give you eta W, okay. So this is a statement that the tensor has a multilinear action on the vector, on the collection of vector and dual vector spaces. Okay, so there is one simple way of constructing a KL tensor, and that is by using K vectors and L dual vectors. Okay, and the way to construct TKL is to use a notion called a tensor product. Okay, so therefore TKL could be defined as K copies of the vector space, which we denote by V1, V2, V3, dot, 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 Vk, tensored with L copies of the dual vector space, which are defined as omega 1, omega 2, dot, 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 omega L. Okay, so if you find kind of looking at tensors difficult, you can think of tensors as just products of appropriate number of vectors and dual vectors. Okay.
Is this true for any general K comma L tensor?
Yes. Yeah.
Oh.
Okay. Now now we'll talk about the tensor product, and this is important because, as I said, that the way these vectors and dual vectors would occur, that is how that arrangement would define indices on the tensor TKL. Okay, so for example, V1 is a vector which has indices say alpha, and Vk is a vector which has indices say gamma. Then T components of TKL would have a first contravariant index alpha and kth contravariant index gamma. Okay, that is exactly the way it would be ordered. The gamma wouldn't occur at any other place. Okay, so in other words, this tensor product is not commutative. You cannot write them any which way you want. Okay. So for example, if you want to construct a new tensor starting from two known tensors, say T1 and T2, suppose these are the two tensors, and they are mixed tensor of rank KL and Mn respectively, then you can construct a new tensor of rank K plus M contravariant rank and L plus N covariant rank, okay, in two different ways, in fact. Okay, and that is either you take a tensor product of T1 with T2, or you take tensor product of T2 with T1. Okay, both of them are K plus M, L plus N tensors, but they are not identical. In other words, T1 tensor T2 is not same as T2 tensor T1. Okay, and the easiest way to see this is to see how this object acts on the vector spaces. Okay, so given that these tensors are mixed tensors, we can try to kind of see the action of T1 tensor T2 on the vector space V1 dot 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 VL dot 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 VL plus N and omega 1 dot dot omega K dot dot omega K plus M. Okay, so notice that given that you have K plus M contravariant indices, this object will give you a number only if you have K plus M dual vectors, and similarly it will give you a number only if you have L plus N vectors. Okay, so in fact, in reality, this object will give you a number when both these conditions are satisfied: L plus N vectors and K plus M dual vectors. Okay, but now when you decompose the action of T1 tensor T2 on to this collection of vectors and dual vectors, then what you find is that T1 would act on first L fellows, okay, because T1 has L covariant indices, okay, and act on first K omegas because it has K contravariant indices, okay. Whereas T2 will do the opposite. That means, well, not opposite, but whereas T2 will do the following, that it will take the L plus 1 to N and pick up N contravariant indices to which the covariant indices will contract, and K plus 1 to M, which are M covariant indices to which the M contravariant indices of the tensor would contract. Okay, so this is the way you would get a number when you have a T1 tensor T2 acting on this collection of vectors and dual vectors. Okay, but we could ask a question, what if I do it the other way around? Okay, by that I mean, instead of taking T1 tensor T2, I take T2 tensor T1. Okay, but if you do T2 tensor T1, then T2 would act on N contravariant indices in the vector. That means it would act on N vectors. Okay, so N vectors means you start with V1, V2, dot, 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 up to Vn. Okay, N may be larger than L, may be smaller than L, depending on that you would cross VL or you will stop even before you hit VL. And T2, and T1 will start from Vn plus 1 and go all the way up to VL plus N. Okay, and similar problem with omega. Okay, so this action of T2 on V1 to Vn is different from T2 on VL plus 1 to VL plus N. Okay, and as a result, the number that you would produce by contracting T2 tensor T1 with L plus N vectors and K plus M dual vectors is different from contracting T1 tensor T2 with the same collection. Okay, and it is in this sense that the tensor product is not commutative. Okay, that means T1 tensor T2 is not equal to T2 tensor T1. Okay, any questions? Is that okay? Okay. So given the fact that components of any given the fact that the tensor can be decomposed in terms of vectors and dual vectors, we could obviously kind of write down any tensor in terms of tensor products of vectors, basis vectors of the vector space and basis vectors of the dual vector space. Okay, so if you have a tensor which has K contravariant and L covariant indices, okay, which is what we call rank K, L tensor, then T can be written in terms of the basis vectors with L dual vectors and K vectors belonging to the tangent space. Okay. Of course, T alpha 1 to alpha L, beta 1 to beta K are called components of the tensor. Okay, so as I said that tensors is a generalization of the notion that we use for defining scalars and vectors. And since scalars and vectors were defined in such a way that they were invariant under coordinate transformations, we'll continue to define tensors in the same fashion, so that the tensors are invariant under coordinate transformation, but their components do transform. Okay, so let's look at how the components would transform under arbitrary coordinate transformation. Okay, so suppose you have a rank K comma L tensor, K contravariant and L covariant indices. Then under the coordinate transformation, it transforms what's in this fashion, which is what's called the homogeneous transformation. Okay, so tensors always transforms homogeneously under coordinate transformation. Okay, and this homogeneity of the transformation property is responsible for the statement that I made earlier, saying that if the tensor vanishes in one coordinate system, it will vanish in all coordinate systems. So therefore, if you have done this computation in one coordinate system, you are done for all of them. Okay. Fine. So this transformation property of the tensor, of course, can be reduced to the Lorenz transformations, and that would correspond to appropriate number of lambdas that would occur. So there would be L lambdas with alpha prime indices downstairs, and there would be K lambdas with beta prime indices upstairs. That takes care of appropriate number of covariant and contravariant indices of the tensor under Lorenz transformation. Okay. Now, so far we have defined tensors as maps from collection of vector spaces to numbers. Okay. But that is not necessarily the only definition. We could also define the tensors in yet another way. And that is to say that a tensor, for example, a second rank tensor is a map from a vector space to a vector space. Okay. So suppose you have a mixed tensor alpha beta, okay, then its action on V beta would give you a new vector, which I have called W alpha, which is just T alpha beta V beta. Okay. Now, since beta is summed over using Einstein summation convention, the object finally carries only one irreducible index, namely alpha. Okay. So one could think of tensors also as maps from vectors to vectors. Okay. So it's another small exercise. You can check that W alpha transforms as a component of a contravariant tensor. Okay. So, so notice that like T alpha beta was a mixed tensor and V beta was a contravariant vector, but this object would have a transformation property as a contravariant vector. Okay. So all you need to do is to kind of go back in this and check how the tensors transformed. Like that, rather here, and use these properties to determine how W alpha would transform. Okay. Okay. Fine. There is another new notion that one defines for the tensors. And of course, the notion of contraction was defined earlier also. For example, omega alpha V alpha was a contraction of indices, contraction of a dual vector with a vector. Okay. But in case of tensors, you can define a contraction of a tensor without using any other tensor or a vector space. Okay. And that contraction is defined by saying that, you can just set one upper index and one lower index of the tensor to be equal. Okay. And if you do that, then the new tensor would be a tensor with rank 2 less than the original rank of the tensor. Okay. So initially, suppose you had a KL tensor, then by doing the contraction, you have a K minus 1, L minus 1 tensor, because one contravariant index would be contracted with one covariant index. In that case, you have a reduced rank tensor. Okay. So the notion of contraction is defined in case of tensors by themselves. Okay. So for example, we encountered T alpha alpha, which we said is not a tensor. Okay. Is an object which is actually a contraction. Here. So T alpha alpha is actually some object that you obtain from a mixed tensor T alpha beta by setting beta is equal to alpha. Okay, and if you set beta is equal to alpha, then you would get del x delta by del x prime beta prime, replaced by del x delta by del x prime alpha prime. And if you do that, then you get this expression, which is precisely what we had obtained earlier. Okay. Fine. So Yeah. So for example, if you define a 3,1 tensor, that means a tensor with 3 contravariant indices and 1 covariant index, then using this 3,1 tensor, we can define a 2,0 tensor by contraction. Okay. And that is done in the following way, that you set gamma is equal to delta. Okay. So this is one way of contracting the tensor, that you set gamma and delta to be the same index. Okay. In that case, the rank of the tensor goes down because the number of irreducible indices that the tensor carries is not 4 but 2. Okay. And therefore you could happily call this tensor a second rank contravariant tensor carrying indices alpha beta. Okay. Components would be carrying indices alpha beta. Okay. Now notice that T alpha beta gamma delta would transform in a particular fashion. We have given that definition. Okay. Use that definition, and remember we also have checked that T alpha alpha does not transform like the second rank tensor. So we know exactly how that would transform. Use that fact also to show that the T alpha beta that we have obtained here as T alpha beta gamma gamma, that object actually transforms like a tensor. Okay. Now, when I said that the tensor product is not commutative, that non-commutativity reflects onto contraction rule here. And that is that if you have T alpha beta gamma delta, instead of contracting gamma with delta, that means setting gamma and delta to be same, you could try to contract beta with, or rather, you could kind of write down T alpha gamma beta delta and try to contract gamma with itself. Okay. Now, again you get a second rank tensor. Again it is a second rank contravariant tensor, but that is not the same as the T alpha beta gamma gamma that we have got. Okay. So this is a reflection of the fact that the second index is acting on the second vector space. Third index is acting on the third vector space. So therefore, if the third vector space is contracted with fourth dual vector space, that is different from second vector space being contracted with the fourth dual vector space. Okay. And it is in this sense also you can understand that the tensor products you used for defining tensors, okay, that product is not commutative. Okay. Now remember, we encountered metric tensor when we defined the metric on the Minkowski space, and we called it eta alpha beta. And eta alpha beta is of course 0,2 tensor. It's second rank covariant tensor, and this second rank covariant tensor can be used to define the inner product between vectors, and that is defined here. Eta acting on V and W is eta alpha beta V alpha V beta. Okay. So similarly, inverse of this metric, which is eta upstairs alpha beta, is a second rank contravariant tensor, okay, which is called 2,0 tensor. Okay. Whereas the Kronecker delta alpha beta is just a 1,1 tensor. Okay. Okay. So we will kind of look at this Levity tensor case and stop today. So epsilon alpha beta gamma delta is a special tensor which is called Levity tensor, and this Levity tensor has a property that it is equal to 1 if alpha beta gamma delta are 0, 1, 2, 3 or any even permutations of 0, 1, 2, 3. Okay, that means you take this labeling, okay, and permute 0, 1, 2, 3 to a new labeling, which could be say 0, 1, 3, 2, or it could be 0, 3, 1, 2, or whatever. Okay, and you ask how many basic permutations are required, okay, to go from 0, 1, 2, 3 to the new configuration. Okay, if that requires one permutation, okay, that would be called odd permutation. 3 permutation, that would also be called odd permutation. Okay, But if it requires two permutations or 4 permutations or 6 permutations, then they will be called even permutations. Okay. Epsilon alpha beta gamma delta is equal to 1 if it is an even permutation, minus 1 if it is an odd permutation. Okay. Now, given that epsilon alpha beta gamma delta could be could be 0, 1, 2, 3, or it's some permutation, only other possibility would be that if alpha is equal to beta or if alpha is equal to gamma or something, any two indices being same. Okay. The Levity tensor has a property that if any two indices are same, it just vanishes. Okay. This is called completely antisymmetric tensor in 4 dimensions. Okay. And of course, there is an analog of this tensor in every dimension. In 3 dimensions, you have a similar tensor where if you write that as epsilon alpha beta gamma, then alpha beta gamma take only three values. Okay. Fine. So I want to leave you with one exercise, and that is compare the transformation properties of eta alpha beta. I'm sorry, it should have been subscript. Delta alpha beta and epsilon alpha beta gamma delta under Lorenz transformations as well as under general coordinate transformation. Okay, and check that eta with alpha beta downstairs is second rank covariant tensor. Delta alpha beta is formally a mixed tensor, but you can check that would actually transform like a scalar. And epsilon alpha beta gamma delta is the 4th rank covariant tensor, which is totally antisymmetric. Okay, so I think I'll stop at this point. Any questions?